good data very soon. Okay, I promise I'm almost done. I just want to highlight that, aside from the work that's being done on the observational side of things, I've also been working to make parallel efforts on the theory side to try to, move beyond this question of mixed and unmixed and use hydrodynamical simulations to understand, realistically what the mixing pattern is likely to be for different kinds of explosions. And I'm lucky to be working on one arm of this project with Harvard's own Paul Duffel. So Duffel and Barnes coming soon. Okay, so aside from the question of our process origins, one other really tantalizing possibility that comes from one other tantalizing possibility that comes from the idea that collapsars produce the R process is that we might be able to use that to learn more about the engines of GRB supernovae. So these are weird supernovae. We think that they're the explosion of stripped envelope stars. They have very broad lines, as you can see. Just as in a kilonova, these broad lines imply a high velocity and a high kinetic energy. All of these broad line 1C supernovae have associated GRBs. No, I'm sorry. All supernovae with associated GRBs have broad lines, but we also see broad lines in cases where there are no evidence for these ultrarelativistic outflows. So there are a lot of questions about exactly what is the engine driving these explosions. So some hypotheses that have been proposed are disk winds, magnetars, the GRB jet itself. But whatever you think the engine is, if you also buy the fact that our process material is produced in collapsar disks, somewhere in this formulation, it seems pretty likely that these different explosion mechanisms might lead to different enrichment and mixing patterns, and that is something that we could, so that is a way that we could use observations of our process material in collapsars to distinguish between different mixing patterns and possibly use that to get a clue as to the GRB explosion engine. Okay, so now I'm finally done. I will just leave my conclusions up here. Thank you for sticking with me. I know I ran a little long and I apologize, but thank you and I'm happy to take questions.
All right, a few questions.
So if you go back to the late time observations of 2017, at what point should you see an effect on the light curve itself?
Yes, so I think that's what we're trying to figure out. It really depends on what you assume about how the R process material is mixed into the supernova. So, I mean, we think it's at very late times, like at least a year, but depending on the relative amounts, it could be more than that. Yes, and also depending on like the spatial distribution. So I guess that's one thing I'm working to more systematically delineate.
Abby, you had a question?
So the different mechanisms that for producing our process elements, they have different rates. And so there is an issue of, I mean, if an event is less frequent, then mixing in the galaxy would not be as complete, or you might have more variation, more fluctuations in the. So the question is, can we get some clues about the rate of the sources from the variation in the R process elements from place within galaxies?
Yes. Yes, we definitely can. I'm not.
By looking at stars, for example.
Right.
That's the argument of the reticulum.
Yes.
Yeah, but
that's.
that's.
If you have large variations in the R process,
Yeah.
of stars in the same galaxy, that suggests that it was
A rare
event
event.
with high yield rather
So
than
how
frequent.
rare should it be? Should it be neutron stars?
Yeah, I mean, it doesn't.
Collapsars?
So collapsars and neutron stars, because collapsars are like 1% of, or I guess I shouldn't even say collapsars because that's a theoretically derived term. GRB supernovae are like 1% of core collapse supernovae, or is that, yeah. So, and so they fall into the same not quite the same enrichment pattern, but they fall into the same rare high yield paradigm as neutron star mergers. Where they differ is, that they track star formation, whereas neutron star mergers happen with a delay time. So you have, yes, I guess you have the same rate yield, but you have a very different.
And less peak. less kick out of the galaxy, so that
Yes.
changes the pattern.
Yes, definitely.
Although if you argue that there was a population of binary neutron star mergers that had a very prompt
Yes.
merger, then they might have a kick, but they're not going to travel that far.
Yeah.
So.
One more question?
What fraction of the neutron star merger mass is released in the jet?
In the jet?
In the jet.
Oh, like you mean the ultrarelativistic
Yes.
jet, or you
I
mean the
thought you made
dynamical?
reference to that on one of your slides.
Well, so I guess let's see. There are kind of two polar outflows that are
Yeah,
distinct, right? So I mean this I would not call the jet, even though it's polar. So like you have the gamma ray burst jet, which will contain almost no mass because it can't be very unloaded or it won't reach the high Lorentz factors.
Sure.
This, according to radiation transport simulations, is somewhere around 0.04 solar masses, which again is why this gets a question mark, because general relativity simulations told us we should expect like 10 times less mass than that. So it's like, how do you, and then it's also weird to have a massive polar outflow in combination with a massive accretion disk. Like those things were kind of suggested to vary inversely from each other. So it's still an active topic of research whether whether there are uncertainties in inferring parameters from models, or like whether there could be some different physics at play that's responsible for launching this outflow.
All right, let's thank the speaker one more time.
Very nice. Thank you.
Oh, thank you. Thanks. Thank you.
And of course, the next one is going to be completely different. No.
Very nice.
It's a bit
Thanks.
Good.
Okay.
Just no, it's now everything is out in the open. There's no way to change. Yeah.
Come on, man. By the way, I don't think the polar outflow is actually polar.
No.
Just so you interesting.
Oh.
I think Brian called it the polar outflow.
No, I mean if you look at the simulations, it's not like pole, but it's preferentially along the poles.
Not any I've seen. I've seen them always be oblate. You just hit some shock and it just flings out stuff actually in an oblate pattern because it has angular momentum. But it's
no.
Yeah. I mean the whole system has angular momentum, right, and it's rotating. And then you hit when they collide, they make a shock that sort of just puffs out. Yeah.
But it's, I mean, isn't it still like it doesn't reach the?
This is the ones I've seen. It's always just a sort of slightly oblate outflow, like.
You mean slightly prolate?
No. This is like
So you actually
Kenta's,
clear
like
out the
Kenta Hodokazaka's. Maybe Davide has a different result, but anyway. Brian liked calling it a polar outflow because, or I don't know if Brian was the first one to start calling it that, but because to distinguish it from the equatorial, the very equatorial sort of stream of stuff.
Right.
But
yeah, I mean, I guess I knew that it wasn't. I know it's not like a.
it's not like a jet, but
confined within a really narrow angle, but I
Right.
still always thought you had more mass at polar. So wait, which are you?
Let's see.
God, Kenta is so productive.
It was stuff he did before 2017. It would have been because it was before the thing was discovered. So let's see. Mass ejection. Yeah, that's a good one. So that's the outflow.
Right, but you have this. Okay, so this is what is their dynamical ejecta though? Is it tidal or is it?
Well, maybe there's a better plot somewhere else, but.
Okay, well that's good to keep in mind.
But you don't ever see for some reason people have this picture of just them squishing together and just having stuff goes like that, which there's really no reason that would happen.
Okay.
It would if two things squish together, you will get an outflow. At the very least, you would get an outflow in a plane or something. But really, you would get it roughly. It's something that's roughly spherical, but it has enough angular momentum still that it becomes kind of oblate. Okay. Anyways, it's fine. Whatever. Everybody does this.
That's, well, because like even in our paper
Yeah.
from 2017, like we have some great.
It's the aspect ratio of either example is like small, is like whatever, close enough to unity that it probably doesn't actually affect anything you see.
Well, so then what do you think about like these? Okay, so yeah, okay. So then is it? I mean, then is it a reasonable approximation to say that the blue stuff is a spherical outflow?
I would say it's a reasonable approximation, yeah. So actually, well, yeah, I mean, if it's the aspect ratio is like, at least like the Kenta got was something like 1.3 or something.
Okay.
And that's like enough that you would look at it in like, because just because of the different surface area, it would be slightly different, but not, you know, not by,
yeah, I guess we always did like this shit, which is what I still have in my head.
right, yeah, I don't even
Okay.
know what is going on there. So that's,
I'm
yeah.
just
I think the reason is because that blue, so what Brian pictures that blue, because he imagines there's this tidal stream, and that's like the
Yeah.
orange, and the blue is just sort of a spherical thing that's
Yeah.
behind it, or whatever, that's, and then like, if you just put the orange on top of that, you'll have like a cone
Okay.
that looks like this, but it's actually basically a spherical outflow. I was actually really frustrated because I asked Brian about this, like, because I didn't understand that terminology. People kept saying the polar outflows.
Yeah.
Like, what are you talking about? And I finally asked Brian about this. Like, what do you like? I showed him like not that paper, but one of the Kenta's papers. And I was like, "You talking about this?" And he's like, "Yeah, that's the polar outflow." I was like, "How is that polar?
Okay.
It's not polar." And he's like, "Well, it's